show you why Lake Geneva is a good lake to gain insights about large lakes in general. So just to set the stage, this is Lake Geneva, and we share a border with France. So the border runs through Lake Geneva in the middle. But more importantly, what I want to show on this image, we have mountains, the Jura, and also the Alps. And they control to a large extent the wind fields that we have over Lake Geneva. And so they come from either the northeast or the southwest. From the northeast, it's called the Bise, and from the southwest, it's called the Vent. So to motivate the study that I'm going to present today, I want to show this graph on the right. So this is at the bottom of Lake Geneva, 309 meters deep. And what you can see, the temperature changes over time from 1970. You can see these gradual changes with an averaging 1 degree centigrade per decade, but there's these periods of rapid increase, about 1.1 degrees C per decade, and then other times where the temperature drops rapidly. So we have gradual warming overlain by episodic rapid cooling. And we can ask the question why this is. Why does it behave like that? In the meantime, the air temperature over about the last century in Switzerland, this is from Zurich, about 0.08 to 0.15 degrees centigrade per decade. So we have at the bottom of the lake much more rapid warming than we have in the air temperature. We can look at also the surface layer. Here we have an increase of about 0.4 degrees C per decade, of course, with a lot of fluctuations. So it's 0.4 degrees on the surface, and then we have 0.1 at the bottom, or these periods, and we're in one of these periods now since around 2012, where it's about 1.1 degrees C per decade. The other big control on the water quality in the lake is the oxygen concentration. And here you can see the dissolved oxygen concentrations at the bottom of the lake since 2012. So it starts off at about saturation and gradually decreases. And 4 milligrams per liter of dissolved oxygen is a typical level for the water quality. And life really doesn't like, a lot of life doesn't like getting concentrations less than 4 milligrams per liter. Now, I contend that if we're interested in water quality, then there's two main factors that we need to understand. One is the energy content of the lake, that is the temperature, how it behaves, also the oxygen content. And I'm quite strong on this because I think everything we can say about water quality is somehow connected to both these factors. So why Lake Geneva? Well, there's a lot of interesting things, including being the birthplace of the science of lakes. That was from Fédérale, but for us today, I'm going to talk about the hydrodynamics. And the hydrodynamics are really affected by several different factors of interest. The lake is too deep for annual winter turnover. That is, we get cold water on the surface going all the way to the bottom of the lake. It's got shallow and deep basins. It's got gently and steeply sloping lakebed areas, and also the flow is affected by Earth's rotation. So we capture all the interesting behavior that you can get in a lake. Shallow lakes, I think, are interesting for other reasons than these. But if we're interested in hydrodynamics, and of course hydrodynamics is really a first order control on water quality in a lake and affected by the heat content, etc., then this will something they study in Lake Geneva. And just to show how the lake behaves, this is from a simulation. We have many of these. We're going to see more later, but this is just to show these flow structures. Because it's Coriolis affected, things want to flow in circles, so we see these gyres. And also we can see a gradual temperature increase as we go from west to east, And we typically get a range over the lake of about 1 degrees centigrade over the length of the lake. Okay, so we have two basins, and these are important. So we have the Petit Lac, which is this one to the left, or small lake, about 70 meters deep, a volume of water of about 3 kilometers cubed. And the Grand Lac, 309 meters deep, it's got 86 kilometers cubed of water in it, so a large volume of water. And other interesting factors, I think, for us today is the Grand Lac, the big lake, has 60% of the water is below 50 meters. I've already mentioned the two major winds, and the water residence time, just based on inflow and the volume of the lake, is about 11 years, with a very, very wide distribution about residence times. That's another topic, but because of the structure of the lake and the currents, the variability in residence time, if we follow pathways of water, is extremely large. Data is very important, and we can't do good science without it. So for us today, we're going to talk about CPEL, which is this International Commission for the Protection of the Water of the Léman. Léman is the French word for Lake Geneva, and CPEL is what it's called. And they have measurements at SHL2 in the deepest part of the lake. So we have Lausanne there, Evian there, and right in the middle is SHL2. And then we see another station there, so the physical station means we go sampling there. But we have MM, which we call mid-lake mooring. We have several years of high-quality data from the bottom of the lake. So it's co-located with SHL2. So SHL2, the data is collected every 2 weeks to a month. It goes back to about 1960. There's a very long time series of data available there. I'm going to show some data a little bit from Bouchillon more. So this is a place called Bouchillon, but there are several sources of data that we have. Another one, we have a platform to the east of Lausanne called L'Explore. So it's a pontoon which has a lot of data, a whole range of measurements. I'm not going to present those today, but we have a lot of data in the lake, and it's going to help us explain this question which I posed at the start. So a few words on water quality. I've already said that the energy content has a big effect. So that means temperature and temperature fluctuations, also nutrient loading, and all these factors to do with nutrients and the growth of organisms which are associated with that are strongly controlled by the oxygen content. So just one example about how temperature can have an effect. So during the day, the phytoplankton are at the surface, and they're growing in the presence of sunlight. And of course, in nature, if a carbon source is there, something will eat it. And for the case of the phytoplankton, it's eaten by the zooplankton, and the zooplankton are eaten by the fish. So during the night, the zooplankton come to the surface to eat the phytoplankton, and but during the day, they want to hide from the fish, so they go downwards in the water column. So their food is on the surface, but they need to hide from the predators by going deep. And so you get this up and down motion. So this is actually showing from acoustic measurements the movement up and down of the zooplankton. And we can look at all the different sizes. We've studied all these. And this is the solar radiation coming in during the day. So it's perfectly synchronized. Now, I want to make 2 points about this. The first one is that, of course, lakes are very interested, lake managers and people interested in the science of lakes are very interested in the biological activity in the surface layers, and they typically measure to 50 meters. This is the first time in lakes that we actually showed that, well, the first 50 meters, things are going on, but actually goes down to about around about 100 to 150 meters. So that's, even though lake science is very old, this point hadn't been noticed before. In oceans, it's well known that the zooplankton excursion can be very, very large. But what we see here, we see the 6.8 degrees contour temperature. And there's different theories about why the zooplankton move up and down, what controls. And one of them is temperature, the other one is the change in light intensity. But if it is temperature that controls it, then the warming of the lake will have a big effect. So this will be an unintended or unknown effect of climate change, is that this biological activity in the lakes will be affected. Okay, so what controls the rate of water movement in the lake? And let me step back for a second. Everything that I'm going to talk about today, if you know Navier-Stokes and you know how to calculate surface energy fluxes, then you know all the science which is involved. That's not what I'm going to talk about today. I'm going to talk about how this well-known theory gives us behavior that we can understand in the lake. So the first thing we want to talk about is the surface heating and cooling, that is the buoyancy, because that controls the vertical movement. And in lakes, the water column will always want to organize itself so that it's stable. So somehow more buoyant water gets moved downwards, pressure will drive it back up. So the tendency of the lake is always to stay stable in terms of the density profile with depth. So if we warm and cool during the day and night or during the seasons, of course, we change the surface buoyancy. So that water on the surface is going to be moving up and down every day and over the year to different depths. So these different cycles have a big control on the water quality, because on the surface there's oxygen, dissolved oxygen. And during the winter, if it gets very cold, all that water on the surface will go all the way to the bottom of the lake and get turnover of the entire water column. So when people talk about winter turnover, they're talking about this recycling, this vertical recycling of water. So it's very important to reset the lake like that. So if you think about it, lakes which are shallow and turn over every year, they reset themselves every year. And in a sense, there's no history, they sort of lose memory. If there's climate change, they'll get gradually warmer, but in terms of reset, they kind of start from zero every year. A lake like Lake Geneva is not like that, because it's very rare that we get the full depth mixing. So the vertical mixing is, so we can see in this kind of plot, so we have temperature and dissolved oxygen. So this goes from August, which is summer, into the fall, February into the winter, and then into the spring. And you can see the oxygen on the surface, we get high concentrations. And during the winter, you can see that the oxygen reaches full saturation, about 10 milligrams per liter. It gets deeper and deeper. And in Lake Geneva, it's somewhere up, typically in winter, it's about 200 meters depth you can get the penetration to. So you see oxygen profiles which are saturated down to about 200 meters. So this is a more detailed picture of what's happening in the fall. And this is the temperature profile. And so we have a high temperature on the surface layer, about 25 meters, a rapid decrease. This is the thermocline layer, and then a more gradual change in the temperature. So why do we get this upper mixed layer? It's simply because it's the day-night cooling, and this is controlled by the coolest temperature at night to first order, and the water will descend to the place in the water column where it reaches the same temperature. So at this point, it's about 12.5 degrees. So this would correspond to nighttime temperatures of about 12.5 degrees. But the upper mixed layer is always mixing every day and night. You get this upper mixed layer and you get these straight profiles. Of course, right on the surface, if you swim on the surface of the lake during the day, hot day, there's all this warm water on the surface. It's held there by buoyancy, so it'll be over 20 degrees C. But even during summer, the nighttime temperature might be 15. So if you dive down a few meters in the lake, you'll suddenly get very cold. The top couple of meters will be warm, and then you get the cold water. And sometimes you can get cold water upwelling to the surface. This is normal due to you get local upwelling, but generally the behavior is exactly like this. So the density increases as the temperature decreases. This is a stable profile. So somewhere I see a temperature which is increasing, then there will be unstable profile and the water will rearrange itself. Now, more importantly, I want to point out that the thermocline is a barrier to thermal mixing. So the steepness of this temperature gradient actually wants to suppress motion across it. And it's simply because of this. If we have a flow in the surface layer and you get a shearing, which is bringing water up from the thermocline layer, so the shearing flow brings water up, that water is more dense, so it wants to move down again. So the steeper the thermocline, the more resistant it is to getting these vertical motions. Now, of course, vertical motions can penetrate, but there's a resistance associated with the thermocline layer. Now, to look at the overall behavior, we can look at some CPEL data, and what you can see here is over an entire year. This is a typical year, and there's a 6-degree contour on the bottom of the lake. You can see over the year, during the summer, it warms up and warms up, but generally below 50 meters, not much goes on. So again, it brings back this question: how can I show data, which is very accurate measurements, showing very rapid increases in temperature, 1.1 degrees C per decade, but all the energy wants to stay on the surface? How do we get the energy all the way from the surface down to the bottom so that we can see this increase in temperature? So CPEL has published data in these nice graphs over many years. So this is the interannual changes in the annual mean water temperature. And what they do is they take the water temperature during the year and plot it at the end of the year. It's quite important. So every point you see is from the previous year. So these are times when they've identified as complete winter mixing. So we're going to analyze what this actually means, and is it what they mean by complete winter mixing. And ideally, an ideal system with complete winter mixing, you'll see a straight line and the temperature profile from the surface all the way down to the bottom of the lake. Or more formally, you'll see a uniform density over the entire depth of the lake. So we can just look at these slopes here. We have 3 slopes in these periods between these full mixing events, because in full mixing, as I said, the lake is somehow restarting from scratch. And we can see that there's approximately this, well, this is the same triangle, so it's showing the same slope, so the same increase in temperature away from these periods where we get full mixing. But not only that, we can just take this same slope and draw these lines, and you can see that in all depth layers, so this is over several different depths, all depth layers, at least by eye, the lake is uniformly warming with depth. Obviously, there's a mechanism here which is not explained by buoyancy, because buoyancy wants to keep all the warm water at the surface. So we can look at this in a little bit more detail, and we can look at the average temperature decreases in all layers in full mixing years. So you look at, as I said, you look at the year before. So at this point here, they say there's full mixing, and in all layers, you can see we get a decrease. Okay, all layers, there's a decrease. So the whole lake has cooled. Makes sense, right? So we get full mixing, every layer must cool down. And so in diagrams like this, we should expect to see every layer cooling as I show here. However, there's some exceptions. And here you can see in that year, the temperature increases. 2012, you can see here the temperature is increasing and then decreasing. So there's some physics here which is different. It's obviously must be different, because otherwise, if it's this full mixing all the time, we would get exactly this behavior, every layer cooling. And we obviously don't get it. We trust the data, there's no problems. So there's some different physics which is going on here. So in Lake Geneva, there's no geothermal or no detected we've looked for this, we can't find any lake bed heating. So all the energy into the lake is coming from the surface. It's 580 square kilometers of surface area. The rivers coming in bring different temperatures, particularly the Rhone, but these are the amounts of the energy content due to that is trivial compared to what comes through the lake surface. And so we did a study on this, and if you know anything about the surface energy exchange, you'll know there's lots of different formulas. So we use different formulas and did a study on this. what we found is the single most important variable is the air temperature in terms of the energy exchange at the surface, followed by humidity, and then the global radiation. But these are in order of what's important. So air temperature, which is changing due to climate change, at least in this semi-empirical study that I'm showing here, if that increases, it's obviously going to have an effect on the energy content of the lake. So what this is rather obvious, but nevertheless, it's something to keep in mind. Why is it necessary to keep it in mind? Because milder winters mean weaker vertical convection. So climate change, people think about things warming up, which is true, but for lakes, what's important is the minimum winter temperature, that the increase of that. Okay, so the whole temperature cycle is increasing. It's not the maximum temperature. It's actually the minimum temperature which controls, to a large extent, the vertical convection. I'm oversimplifying a little bit, but nevertheless, this is a strong control on the behavior. The other thing we need to think about is the mechanical forcing, and that is wind. People swimming in the lake may do something, or boats, but the mechanical forcing that they impose is, again, trivial. It's the wind that blowing across the surface. And typically, the wind blowing across the surface will move the water on the surface of about 1 to 2% of the wind speed. And so again, it's an important thing. The wind comes in the surface, but it has effects in the entire lake. And it's a bit anti-intuitive to think about this. What blows on the surface actually affects the entire lake, not just the surface. Just by surface shearing, I think if you do an estimation, this can affect down to maybe 40, 50 meters in this lake in weak stratification. But we get effects all the way down to the bottom of the lake, as I shall show you. So these are the two winds. So this is from measurements at Saint-Pré, which is this area here. So we can see that we have the bise and the vent, and we have typical wind speeds, around 10 meters per second on the surface. This is very typical. So to give you an idea about how lakes respond to wind, I want to show you a movie here. And this is a movie taken in December, so it's weak stratification or weakish stratification. And we're just looking at a lay here. We've got a temperature of 6.052 degrees C. So it's this is the Grand Lac in the basin. It's the surface. We're looking at the movement of the surface. Let's start it. We'll see how it behaves. And what you should look at is just the complexity of this motion. So this is well into the depths of a couple of 100 meters down. So you see the sloshing around in the Grand Lac basin. You get water moving up in the Petit Lac. It sloshes there, and it goes back into the Grand Lac. So even at 200 meters depth roughly where this started from, you get this very complex behavior. So just to summarize, we see significant upwelling. So the water comes all the way up into the Petit Lac. We get exchange. We get wave-like motions, longitudinal sloshing up and down the sides of the lake. While I'm here, I'll just point out that you can see the lake is very steep edges here because it was formed by a glacier, and the glacier carved this out. And on this end, we get a very gradual sloping lake bed. So we get two different behaviors. We've got very steep sides and gradually sloping lake beds in this lake. So we did a study on the exchange that we get just due to the wind forcing. And so this is the lake before the wind on the 16th of January. And we have a site at Bouchillon, where I showed you before this location. And we're taking transects. And we have this 6-degree water from about 200 meters deep. And after the wind, you can see what's happened. Look at the surface of the lake. All this cold water has come from 200 meters. It's come to the surface of the lake. Okay, so this is after 3 days after a wind, a typical wind, a typical vent. This is the behavior. It brings this water up from 200 meters. And you can see here, this is showing this water coming up to the surface of the lake. Okay, and it actually sits on the surface, gets oxygenated, but it's still cold, it's warming up a little bit, and then it'll gradually go back down or sink back down. So this is in winter, so it's 19th of January. This water comes to the surface and actually moves along the northern boundary of the lake. I'll show you something here which is affected by this cold water coming to the surface. So this is the basin scale motion, which has a very big impact on the water quality because it brings water up and it takes it down. This happens all the time. We get these winds very regularly, and this upwelling and downwelling is very common. So it's a significant mechanism for mixing, bringing oxygen to deeper layers in the lake. Okay, so what happens somewhere else in the lake? This is an interesting image. So we have a camera mounted on to the east of Lausanne. It's mounted on a steep slope and it's pointing on the surface of the lake. And you can see on these slicks on the surface, they're biosurfactants, because these bacteria that live in the lake, they produce these biosurfactants. And you can see already there's something going on. We get a big streak here, and then you get all these small streaks. Okay, so there's a wind blowing from right to left, and this movie just shows what happens to these slicks. Now the camera, we can control it remotely, so it changes the image, but it's from the same place, but the camera moves a bit. And on this day, my team was out there, we're taking measurements about what's going on in this area. So you can see what's happening with these slicks. They start on this side. The slicks on the surface, they come to the big patch, this long patch, and they don't continue anymore. It's like a roadblock of some sort. And on the downstreams, or the downwind side of the patch, you can see instabilities caused by differences in surface tension, because the biosurfactants are much weaker surface tension than the water. Okay, so this behavior goes on actually for several hours. And what we see is the large slick in the middle, which is about 10 kilometers long, just gets wider and wider, extends right into the lake. So you think, why does this happen? And just think for a second, why does this happen? It's just weird to have this thing in the middle of the lake. There's no magic, it's physics, but nonetheless, it's actually a surface manifestation of what's happening below the surface. Let me explain. So we have two images here. We have a satellite image and a numerical model, and we just superimposed here where the slick is. So from the satellite, this is temperature. Our camera now was on the side of the lake there, was looking down that direction. So the wind in this image is going from left side. So this wind is blowing this cold water in this direction, and it reaches warm water. So because it reaches warm water, the water on the surface dives down. And because the biosurfactant is less dense, it stays on the surface. So it just collects at this place. So this long slick is actually telling us where the cold water ends and the warm water starts. And this is, you can see the simulation. It's not perfect, but the simulation gives us behavior. This is very typical behavior in Lake Geneva. Normally, you see these slicks on the surface. You think, what on earth are they showing? But this is one case where it shows something which is definitely displaying what's happening underneath the surface of the lake. Okay, now I want to go back to this pattern we saw in 2012, the two exceptions. Okay, we had complete winter mixing, complete winter mixing. Well, I can't say much about 1979, but for 2012, we have a lot of data, specifically at the location of SHL2, where these measurements are from. So we can give our measurements and add these together to get something interesting about the understanding of what's the difference between 2012 and other years. So just to remind you, the layout of the lake, we have the shallow area here, the Petit-Lac, we have this gradually sloping lake bed, and we're going to be looking at measurements in the middle of the lake. Okay, so 2012, we had an exceptionally cold spell in the lake, and it went down to about -10 degrees C for a period from 3 to 13 of February. And before that, the temperature was, this is typical, around 0 to 5 degrees C. This is typical for the area, but very, very rapid cold period. In fact, it was so cold, I remember in the eastern end of the lake, a very calm day, in one of these days, it was so cold that there was a cloud of water vapor just sitting on the surface of the lake. It was so cold that so the lake water was warmer than the air, and it just spontaneously formed this water vapor on the lake. It was like you didn't see water anymore, you just saw like a cloud, white cloud on the surface of the lake, which is the water vapor. Okay, so now we can again just look at data and we can interpret a lot. This is the value of good data, I must say. So this is CFL measurements. Let's look at first at the temperature. We have 11th of January, 23rd of February, 8th of March, 19th of March. This is their regular temperature profiling periods and times that they're doing this. But we can look at just, first of all, 11th of January. You see the temperature profile starts on the surface a bit over 7 degrees, gradually decreases, and then about 180 meters, it gets fairly constant. 23rd of February, it's the blue line. You can see that the water has cooled. It's a straight line, you see. It's cooled down to about, let's say, 5.4, all the way down to about 220 meters. And at 220 meters, it goes back and joins the line from the 11th of February. Okay? And then it goes, and then it decreases again below. So 11th of February, we had around 5.5 degrees at the bottom of the lake. And then 11th of January, and then 23rd of February, it's gone down, down to 5.2. Again, this is not consistent with vertical mixing. It can't be. This is vertical mixing, this part here, down from the surface down to 220 meters. This is what you look for, fairly straight line. Then it goes back, and then you get cold water at the bottom of the lake. So if it's not vertical movement of water, and since there's no cooling and heating from the lake bed, the only other explanation is lateral movement of water coming in there. So this is in the middle of the lake. Why do you get lateral movement at the bottom of this big lake, more than 300 meters deep, and you get lateral movement of water, not from the surface? Okay, the oxygen story is basically the same. In fact, they're a lot less frequent, the measurements. And so it shows, let's start from the 11th of January. There's the 11th of January line. The black line gradually decreases to below 4 milligrams per liter at the bottom of the lake. And then you can see it reaches a fairly uniform profile, towards 10 milligrams per liter. And it gets down to this point around 200 meters or so, and then it increases. So this is a straight line joining 2 points. It's not a straight line, there's a point here and a point here. So you can see the value goes down to something very close to the value in January, and then it increases again. Again, this can only happen if this is winter biological activity. There's some generating oxygen in the water column. So this is water coming from the surface, moving laterally to the bottom of the lake. It's the only explanation. And we can confirm this. It gets more interesting at the middle of the lake. We look at our detailed measurements. This is our installation with Lake mooring. We have temperature measurements at 180. This is from the bottom. This is from the surface. 120 meters, 180 meters, 240, and 309 at the bottom. And you can see between 3 and 13th of February, all the temperature profiles are sitting up here from about, say 5.6 to 5.8 degrees. And then you can see this gradual decrease in all the layers. The really interesting one is the bottom layer, 309 meters, and you can see this very, very erratic behavior at the bottom of the lake. Whereas the upper layer, let's look at 120 meters, you can see it's just a gradual increase, decrease at 120 meters. So again, there's obviously different physics here. 120 meters, you get a gradual decrease. 309 meters, it's something crazy going on there with this very erratic behavior. We can explain it by this movie. And so this is showing temperatures. It's a full simulation of Lake Geneva for this period. And it's just looking at the bottom It's about 5 meters on the bottom of the lake everywhere. Okay, so this is where it started on 24th of January. So you can see it's colder on the bottom. Okay, it's cooler and the warmer water sitting on the edges of the lake and in the Polytechnique. So let's start this movie. And you just see cold water forming in the Polytechnique. It flows downwards into the Grand Lac, moved right by Coriolis. And look where the X is in the middle, where the measurements are, you can see these eddies moving through. Okay, so these large eddies. So this cold water forms in the shallow part of the lake, in the Polytechnique. It cools down and falls down the slope, affected by Coriolis, forming these eddies, and it causes these very erratic temperature measurements that we see. Okay, so all these are perfectly well explained by these eddies which are coming through and swirling around on the bottom of the lake. Okay, because of the configuration of the lake, and many lakes have shallow areas and deep areas, it happens all the time. It's almost universal, I would say, because lakes are not like swimming pools. They have rather interesting morphologies. And this lateral transfer of water into the Grand Lac is regular. Happens all the time. It doesn't have. This is a major event because it was so cold. That was a very unusually cold event. But it's always cooling more rapidly in the shallow parts of the lake. Anywhere it's more shallow, the heat content is less, and the surface energy flux is roughly the same. So if you're taking energy away everywhere the same, so the heat content is decreasing at the same rate. Obviously, in the shallow areas, it gets colder. Lake Geneva never freezes, not a lake like that. But on this, sometimes when it gets really cold on the edge of the lake, some ice will form. It gets cold enough on the edge, but never in the interior of the lake. Okay, so we can look at this in some detail. We have models. You can do lots of interesting things. So what we do is we divide the lake into these areas. And modeling, we can chop the lake up into these different areas and say, what's really controlling the temperature at the bottom of the lake? So we have the Polytechnique here is one area. We have all these shallow areas, and we can distinguish them. And we took the depths less than 50 meters, I think, for this, or maybe 30. It doesn't matter. We captured these areas. And then we can look at the contribution to the heat content in the deepest part of the lake. So we have below 150 meters and below 190 meters. And we have the part due to the vertical convection. We had the lateral advection from the Polytechnique and the lateral advection from the shallow areas of the lake. And let's just look at the bottom one. Maybe it's simple enough to do that. You can see that the vertical convection actually increases the heat content. How is this possible? How is it possible for cold water moving from the surface, this is vertical convection, to actually increase the heat content at the deep part of the lake? It's one of these curious things, but if you think about it, it's quite obvious. When water moves down, it's actually pushing water out of the way, so there's a temporary increase in the heat content as the water is moving down. At the same time, water is moving up, but you get this temporary increase. And you can see it's a transient effect. So this is the displacement of the water, of the warmer water down. But you can see that below 190 meters, after this transient, it's got nothing to say about the heat content in the deep part of the lake. The lateral advection, on the other hand, from the Polytechnique, has a big effect. Okay. And so this really shows the effect of this Polytechnique in this event, a very major effect. There's a small amount of cooling in the deep part of the lake from the shallow areas, the littoral zones, but not much. It's really all due to this water coming from the Polytechnique. Now, at the higher elevations or below 150 meters, the picture is not so dramatic, but it really doesn't change a lot. It's you get this more of an effect of the vertical convection, but there's still a large effect of the lateral advection coming from the Polytechnique. Okay, so that's everything I've been talking so far is well, more to do with what's the role of the vertical convection. But I already showed one example of basin scale motion. And basin scale motions are hugely important, and they have effects at the basin scale and smaller scales, as we're going to see. So just to bring everyone up to speed, when the wind blows in a lake or across any water surface, it pulls the water up in the downwind direction, and then when the wind stops, it relaxes, and the gravity wants to make the water go back to a neutral position, and it's called seiches, because it's rocking. It's a word that means rocking. And Fédérale was the first person to prove this happens. So you see a system here, the water piles up and then it starts to rock. Okay. Now, because we have a large lake, Coriolis wants to move, in the northern hemisphere wants to move the water to the right. That causes these circular motions. So we have these wind events all the time, causes setup, and then you get this basin scale motion where it's rocking, and it causes waves, all sorts of interesting waves. One you may have heard of is Kelvin waves. These act along the longitudinal axis of the lake in northern hemisphere. They're shore hugging to the right, and they set up an anti-clockwise motion. So you get a wave which is moving around the edges of the lake. It's a Kelvin wave. And another one, which is less obvious, it's more to do with the thermocline Poincare waves. They're dominated by the transverse axis of the lake, and they form cells along the lake. And they also move in the clockwise direction. The size is controlled by the lake width. There's lots of other waves which are formed, but these are the only ones we need to concern ourselves with here. So we can show the effect of those waves in these movies. If we integrate the temperature profile, we can look at the effect on the thermocline moving up and down. So when these waves move, they move the thermocline up and down. So this is how we can detect them. So this is from a numerical simulation. The Lake Geneva Kelvin wave has a 5-day period. Poincare waves have a 14-hour period. So you can see here, just your eye will catch this motion. So integrated potential energy, just think of integrating the temperature. So it's capturing the movement of the thermocline. So you can see this slow movement of the Kelvin wave around the lake. And this one, you can see different cells. These are the Poincare waves. So this is all coming from the numerical simulation. Okay. In the field, you can detect these waves during pressure measurements or temperature measurements, or both, combinations of both. But numerically, it shows these patterns quite nicely. Okay, so I want to show one manifestation of a Kelvin wave. We have, for several years on the mountain here, we had a camera pointing and getting imagery of the entry of the Rhone River into the lake. The Rhone River is by far the biggest contribution to water in the lake. And of course, it goes all the way through France. But so Lake Geneva is just part of the Rhone River, if you want to think about it like that. So let's look at these images. So these have been rectified, so we're vertically downwards on the surface of the lake in this area. And you can see all the sediment coming in. Now, the Rhone is always colder and always carrying quite a sediment load. So a typical behavior when there's nothing much going on, you get a diving of this more dense water, and it forms a triangle, and then there's some unusual behavior where it comes up to the surface. But this is very, very typical. By the way, there's a fence around here. That white line is a fence where they use to capture debris coming into the lake, so it doesn't, like wood, so it doesn't lodge itself in other parts of the lake. So in any case, 4 o'clock in the afternoon, something's changed, but still, yeah, okay, it's more or less the same. And then at 5 o'clock, you can see a deviation of this pattern on the surface to the right. And then at 6 o'clock, there's a lot of mixing, there's really strongly pushing to the right of the Rhone plume. 7 o'clock, 8 o'clock, and you can see this, this behavior. Again, it's a very simple behavior. In fact, if you know that a Kelvin wave is coming through then, and we did simulations of this, we had field measurements. And we could see very clearly, you read very well, you could see this Kelvin wave coming through. In our field measurements, this is the passage of the Kelvin wave. It's pushing the rate of discharge strongly to the right. And also the water velocities that we measured increased to about 0.5 meters per second, more than 5 times greater than the background current. So these waves coming through actually cause a lot of water movement and mixing. You can see here. So a lot of mixing that happens due to the passage of this Kelvin wave is shown very clearly by the images here. But it gets more interesting than that. So as I already showed you, we have at the bottom of the lake, we have the instruments, and we can look at what's happening in the deepest part of the lake. And you can see this pattern here. We're looking at the temperature. You can see that you get these regular pulsing of temperature. And within this, say, longer period pulsing, you can see lots of small pulses sitting in the middle there. This is in the middle of the lake, a long, long way from the shore, Kelvin waves. Everyone thinks that Kelvin waves are actually near the shore, and the magnitude is, in theory, decays exponentially as you get away from the shore. So here we see in the middle of the lake this regular patterns coming through. So it's a signal, and we can easily decompose this signal. So now we look, the previous slide was temperature. Now we're looking at the eastern velocity. At the eastern velocity, we can see, first of all, the bottom layers are always in motion. And remember what I said, that on the surface of the lake, we have winds around 10 meters per second. 1% of that is about 10 centimeters per second on the surface due to the wind. But on the bottom of the lake, we have velocities up to about 5 centimeters and even more we can show in our measurements. So all the way down, long way down the lake, we get velocities which are comparable at least to what's happening on the surface of the lake. Because it's a signal, we can easily do a Fourier decomposition, and then we do a bandpass, so we can just look at what's happening at certain periods. So we look for the Kelvin wave period. Okay, you can see it's matching fairly well what we see in the original signal. We can also look at the Poincaré wave period, 14 hours for Lake Geneva, and you can see this blue line. If we add the blue line and the black line, you can convince yourself we capture a lot of what we see in the velocity signal. So just by these two components, of course, there's lots of other frequencies which are involved here, but the Kelvin wave and the Poincaré wave actually explain a lot of what we see in the velocity signal. The temperature and velocity oscillate together. The theory of Kelvin waves, I think the temperature and velocity, if I recall correctly, they're 90 degrees out of phase. I don't think this is 9 degrees. So something interesting is going on here with the temperature and velocity, but it's normal that they're out of phase, but the oscillations are synchronous. So again, this just shows that these wave motions, Kelvin wave and Poincaré wave, explain a lot of what's going on in the bottom of the lake. So how do these internal waves transport heat downwards? Because this is crucial. It's the internal waves which are actually transporting heat. Now, as I said, I've only talked about Kelvin waves, Poincaré waves, but there's a lot more to this topic. But there's internal waves in the lake, the same as there are surface waves. And they cause mixing through internal friction and dissipation, get wave-induced motions, including wave breaking. Internal waves in lakes and also to the ocean can be very large because they have these gradual density gradients, much larger than you see on the surface. And they can break, they can shoal on the lake bed, and all these cause mixing. And this explains this constant gradual warming. Away from these boundary effects, you know from linear wave theory that a particle with a linear wave makes a circular motion. And what circular motions do is cause a mixing. And so just think of all these waves causing motions, and it causes mixing. It happens everywhere in the lake, and it explains why we get everywhere in the lake the same long-term, or more or less the same long-term temperature increase in all layers in the lake. And just to show you what happens, to give a more intuitive picture of this, this is a simulation of the lake, and we're looking through the lake through the entire width of the lake. It's not just a slice, it's through the entire width of the lake. So it's captured, and it's on the longitudinal long axis of the lake. So here's the Fertilac, here's the Grundlac, and these are all particles which have been seeded in the upper part of the lake. It starts in rather weak stratification, 21st of December. Let's see what it does. And this is just to give an idea about these particles are just tracing water movements. Okay, so there's no mass, they're massless particles, just to give an idea of visualization of how water can move in the lake. And my argument here is what you're seeing, this penetration of particles actually reaching the bottom of the lake. This is just through these basin scale motions of the lake. Okay, so the simulations are showing us that these basin scale motions are causing these particles of water, which are tracking the movement, to penetrate all the way to the bottom of the lake. Okay, it's just to give an idea about why the mixing just doesn't stop. We have all these wave motions, all these movements, it causes mixing. And because these particles are actually coming from the surface downwards, they're bringing the heat, it's showing that the heat is moving downwards also. So this is despite having a thermocline, moving against the regular expectation of motion. But this is universal behavior, not just here, but also in other lakes. Okay. So let's round things up a little bit. Is warming in the deep part of the lake caused by climate change? Actually, no, because it's always warming. It was always warming. It's nothing to do with climate change. It's warm anyway. The effect of climate change is actually due to the cooling, due to vertical convection. It's going to weaken. And of course, if you have high temperatures on the surface, then eventually that energy is going to make it down to the deepest part of the lake. So these mechanisms just keep moving the heat downwards and would warm Lake Geneva. But we have big factors. We have differential winter cooling, basin scale motions initiated by wind. So both of these things will continue to attenuate the effects of climate change. So the mechanistic picture for Lake Geneva is the vertical convection will continue to driven upwelling and downwelling is probably unaffected, but if you have warmer water surface, then it would have an effect. The lateral inflows, which I showed, are a strong event, but these are happening all the time, so they'll continue to move, inject water, cold oxygen-rich water into below the vertical convection depth, most likely. And these internal waves will, to the effect of those, as I've already said, will continue unaffected. So this is an engineering audience. So I want to say there is a way that we can use this for engineering, although we haven't done this in any detail, but I think the idea is reasonable. You can think of a barrier on the bottom of the lake between the Fertilac and the Grundlac on the confluence there, several kilometers across there. And imagine a barrier which can be inflated and deflated. The problem with the Fertilac in the normal winter, the coolings are carrying all the time, but we want water into the deep part of the lake. So we want to capture a big amount of cold water in the Fertilac and then open the barrier and let it go into the deep part of the lake. So the idea would be just let, in a regular winter, for that water to cool down, time and collected enough to let it through into the Grundlac to go to the bottom of the lake. Otherwise, there will be exchange in time, and probably that cold water would stay in the upper part of the water column. Okay, so I've worked on lakes for some time, and I have some thoughts on how to assess large lakes. First of all, as I contend the heat content and oxygenation of first order controls. And I think these are factors which are ignored too often in large lake studies. Measurements are most commonly single vertical profiles. They're important. Okay, but by themselves, even though I've showed you we can get a lot, but we couldn't explain everything. And in fact, the reason, at least in my experience, we have a lot of understanding about Lake Geneva is because we have 3D modeling, which is very, very trustworthy. I know the limitations of modeling, anyone that's involved does, We have very trustworthy modeling of Lake Geneva, and it's a fantastic help in understanding our data. And the very common 1D modeling of lakes that really explain the heat content, oxygen status of large big lakes, because you've seen all this lateral motion, basin scale motions. They can't be they can't be explained by 1D modeling. I've referenced several papers here. These are the ones which explain the science about certain results that I've shown in this talk. With that, thanks for your attention.